I'm just going to kick off the session now. So thank you very much for coming along. My name's Stuart Johnston, and I'm the interim program leader for networks at RACE 2030. And it's my pleasure today to introduce and chair this session on the energy transition. As you're all aware, the energy sector is currently in a state of flux as it transitions from fossil fuels to renewables, and also we are moving towards decarbonising the wider economy as well as part of that process. As Australia's energy sector moves away from fossil fuels and tries to accelerate decarbonisation, governments, industry and consumers are all going to be challenged in addressing the transition in transformative ways that are sustainable, ensures reliability, so that energy is available when and where it is needed, but is also finally affordable for consumers and customers as well as part of that process. So for this session today, I've got 4 great speakers who will be discussing each different components of each of that transition. The speakers today, we've got Angela Simonska, who is a PhD candidate from the University of Melbourne. We've got Professor Rosalind Archer, who's head of school at the Engineering and Built Environment at the Griffith University. Yusan Hu, a PhD candidate at the University of Melbourne. And Subok Yon, a PhD candidate from Monash University. What we're going to do is each speaker will have 10 minutes. We're going to be quite tight on that. And then we'll have time for 3 questions after each speaker, with the idea at the end we'll get all speakers back up on the table for a panel session. So I'll start off with Angela.
All right, thank you, Stuart. So hello everyone, thank you for joining this session. My name is Angela Simonovska. I'm a PhD student at the University of Melbourne, and today I will present the topic related to electrical model-free optimal power flow for PV-rich high voltage, low voltage distribution networks. So in today's presentation, the outline is the following. So firstly, I'll bring up the context of today's presentation, followed up by the research question. Then I will explain the methodology, followed up by a case study, and then in the end, I will just present the key remarks of today's presentation. All right, so let's begin. So with the growing amount of distributed energy resources, such as residential solar photovoltaic PV systems, there are a lot of issues, especially voltage rise issues at the customer premises due to the exceeded amount of reverse power flows, but at the same time of the solar photovoltaic PV systems. Therefore, there is a need for DR orchestration or for real-time management. Now, the DR orchestration means to orchestrate controllable elements, and there can be dozens to hundreds of controllable elements, depends on the size of the low voltage network. Therefore, it means that advanced techniques are needed. One such technique is the AC optimal power flow. Now, the AC optimal power flow has shown great potential for this purpose. However, the AC optimal power flow requires 3-phase detailed low voltage network models, which means knowing the topology, knowing the impedance, knowing the phase connectivity, etc., which in reality it's not readily available for most distribution companies. Therefore, alternative solutions are needed. On the other hand, this is a challenge. So on the other hand, the smart meters, the rollout of smart meters has shown great potential for data-driven approaches. Now, what if instead of running power flows, we use a machine learning method? What if we use neural networks such that for the same objective function, we can actually use the neural networks equations in order to calculate the control set points of the controllable elements? Well, that is actually the research question. The research question is, can we use machine learning methods to actively calculate the optimal set points without having the electrical network models? To answer to this question, we are proposing an electrical, model-free optimal power flow. Now, depending on the engineering problem, different objective functions can be adopted. but we are using the maximization of the PV generation of the customer PV systems in this case. Now, the main difference is that instead of using power flow equations, now we use the neural networks equations. Now, just for those that are not really involved into the neural networks, so as you can see in the figure, there is a neural network where on the left-hand side, there are the inputs. Now, in this case, we are using the historical smart meter data, which means the active and reactive power, as well as the head of the feeder voltages. Then, in order to calculate the neurons which are in the hidden layer with the letter Z, we are using an activation function, and then further we continue in order to calculate the voltages of the customers. In this example, it's given just for a single household. Therefore, with the number of customers, the number of neurons increases for the inputs and the outputs. Besides the neural networks equations, we are using the available PV resource, as well as the thermal limits and the voltage magnitude limits. All right, so the case study for this methodology is implemented on a integrated high voltage, low voltage network. Now, as you can see, the high voltage network is a Victorian high voltage network that is from 79 distribution transformers, for which we are taking 20% of PV penetration. Whereas the low voltage feeder has 70% of PV penetration and 22 which means that the low voltage feeder consists of 31 single phase customers, which means that 22 customers have PV systems. Now, with this kind of scenario, whereas there is 20% of PV penetration for the high voltage network and 70% of PV penetration for the low voltage feeder, we have voltage rise issues as shown in the figure on the bottom. Therefore, we need to calculate the set points. Now, this is for a summer day, which is January, and you can see that the time is from midday, 12 p.m. until 6 p.m., where the voltage rise issues are really significant. And the installed capacity is 5 kilowatts per customer. Now, in terms of the characteristics of the neural networks, as I previously said, depending on the number of customers, the number of inputs increases. Since we have 31 residential customers, we have 65 inputs, which means 62 depending on the active and reactive power of the 31 single-phase customers, plus the 3 voltages of the head of the feeder per phase. In terms of the outputs, since we have just 31 single-phase customers, we have 31 voltages. In terms of the hidden layer that is used, we use an activation function, which is the tangent hyperbolic, and for defining the voltages, we use the linear activation function. The resolution in this case is 5 minutes resolution, which means 288 points per day. Now, in order to assess the accuracy of the electrical model-free optimal power flow, firstly, we need to assess the accuracy of the neural network performance. Now, the neural network tries to calculate the voltages, and therefore, the first step is to assess the accuracy of the neural network. As we can see from the root mean square error, the average deviation and the maximum deviation, the values are less than 0.1 volt, which means that the neural network achieves very accurate performance in calculating the voltages. Now, once we have the neural network, we are performing the electrical model-free optimal power flow. For this case, we are observing 2 metrics. The first one is the aggregated PV generation. Now, in these 3 figures, I'm showing the aggregated PV generation per phase for the observed time interval. You can see that with the red color is the output from the model-free optimal power flow, whereas as a benchmark is used the conventional AC optimal power flow with the blue line. And in the periods from 4 p.m. until, for 2 p.m. until 4 p.m., there are very small deviations, where for the rest of the part, they are exactly matching, which means that the proposed approach calculates extremely similar aggregated PV generation as the AC optimal power flow. Now, going into details for the individual calculated set points, as you can see in these tables, I will show you which customers have been triggered by the AC optimal power flow in terms of which one had been curtailed, whereas the rest of the customers that are not shown are generated at their maximum available PV resource. At the top is the result from the AC optimal power flow, whereas the bottom is the model-free optimal power flow. As you can see, the same customers have been curtailed, and the differences in terms of the curtailment from the AC optimal power flow and the model-free optimal power flow in this case is around 3 kilowatts. If we move on to other time periods, so another time instance, you can see that they are exactly matching, whereas there is just less than 3 kilowatts difference. Then we have the exact behavior with the next time instance, and if I move on, you will see that the behavior is very, very similar or exactly the same. Now, in this case, as you can see, only one customer has been observed by the model-free OPF, has been curtailed, but that curtailment is less than 0.1 kilowatt. That means that the proposed approach calculates very similar individual PV set points as the conventional AC optimal power flow. Lastly, the voltage profiles of the selected day with 70% of PV penetration for the low voltage feeder. On the left side, you can see the voltage profiles without having the PV set points, whereas in the middle is when the voltage profiles after running the electrical model-free optimal power flow. On the top right, we are using the produced settings in order to run a power flow now, just to see how whether these settings are correct or whether we will have voltage problems after using these settings. As you can see, the behavior is exactly the same as the electrical model-free optimal power flow. Therefore, we have no more voltage problems. And in terms of the computational time, the proposed approach is 6 times faster than the conventional AC OPF. Well, this brings us to the key remarks that with the high DER penetration, there is a need for advanced techniques. Now, even though the 3-phase AC optimal power flow shows great potential, it requires the network models. On the other hand, the electrical model-free optimal power flow calculates optimal PV set points which are extremely close to the AC optimal power flow. At the same time, it doesn't require any knowledge of the low voltage network model, which means it's very cost effective. And it produces a solution within the operational control cycle, which is less than running a power flow. However, there are still challenges and ongoing work for this part, and that is to perform the approach without the need for head of the feeder voltages. Thank you so much for your attention, and before I finish, I want to acknowledge my supervisor, Nando Ochoa, as well as my collaborators, Vincenzo and Arthur, and my co-supervisor, Tansu. Thank you.
I'd like to invite anyone who's got any questions. Please come up to the microphone.
Thank you very much. My name is Ibrahim from ISF. So just a quick 2 questions actually. So we know that machine learning needs, so the accuracy of machine learning or deep learning in general, it requires, it depends on the volume and the accuracy of the training data. So I believe at some point to use the machine learning to predict the PV settings of the inverter settings, you should at some point to run the power flow or optimal power flow with the models to get the training data, to train the models to be able to find the new settings values. Because machine learning needs training data to train, like different customer information and data. These are the settings. You train the model to get the optimal answers. This is one thing. The second thing, once we talk about the optimal power flow, so are we optimizing something based on the power flow equations? So how machine learning do the optimization for that? So it sounds like you're predicting some settings based on a previous optimal power flow studies that you use to train the models. So just to clarify on these 2 points, if you can do that. Thank you.
All right, so exactly the opposite of what you said. That's what you see in the literature. You have a lot of power flow equations, but no, our case it's completely different. We do not use any power flow equations. We use the historical smart meter data. In terms of the volume, we use just 3 weeks of historical smart meter data, which is enough to train a neural network. Therefore, by only using the active and reactive power and the voltages, the neural network has been trained. Once the neural network is trained, in terms of, we check the accuracy, of course, and then on top of that, we use those equations in order to run an optimal power flow. Therefore, it's not based on previous power flows, or we don't train the neural network to learn previous settings. It is based on the inputs, which are the active and reactive power, and therefore now in the optimization problem, we are using the equations to calculate the voltages such that they are not exceeding the maximum limit, and we want to calculate the PV set points through it. At the same time, we also observe the thermal limits. So the power flow equations, as you said, yes, that is important for the AC optimal power flow, but in this case, it's based on the neural network equations. I hope that answers your question.
So the limits, you're calculating them using the equations of the workflow. So you're just using the artificial track to predict something, and then to check these limits within the predefined constraints. So you have some equations to set that or to calculate that?
No, the equations are the ones that I just showed in the methodology. So it's just the available PV resource, the thermal limits, the voltage, the thermal limits, customers' thermal limits, the voltage limits, and the neural networks equations. Nothing more in terms of the power flow, power balance equations, etc.
Has anyone else got something they'd like to ask?
Thanks, Angela. That's really interesting. Ed Langham from UTS. I was interested. You did this with full smart meter coverage, and you're doing it in Victoria for that reason. Can you do this in patchy coverage of smart meters in other states? And if so, yeah, what do you know about that at this stage?
All right. So the part where the neural network is involved and trained with the smart meter data is actually the work of my colleague. What he has been doing lately is where there is a partial smart meter coverage. I do not know what is the lowest percentage of coverage of the smart meter data, but what he has discovered is that it really depends where it is the location of the smart meters throughout the low voltage feeder. So it's not the same if, for instance, we're talking about 40% of smart meter data, and if everything is at the beginning of the low voltage feeder, middle, or at the end. If it's dispersed throughout the feeder, there may be better results. However, if we talk about just at the beginning of the low voltage feeder, then it's not very certain that we will have the results for the end. However, that's not my work, that's my colleague's work. So yeah, you should check his papers and reports.
I'll go for one last question if there's anyone's got one.
Can I add
One more.
Yeah. So what about the what if scenarios? So now with the once we have a model-based approach, we can do what if scenarios. If we don't have these models, for example, if you need to coordinate the inverters with tap changers, with batteries, with electrical vehicles. So with the model-based approach, I can do that because I have an access to all the equations. What about the model you develop? Can that doing this, like if we have several scenarios?
So when you said with the model base, you have access to all of this, that means that the distribution companies need to have all the available information in terms of the changes in the networks, right? So that was the main the main topic of my my presentation today, is that information is not really available, and in order to recreate that model takes a lot of time. Where in this case the historical smart meter data is there, the smart meters will again just take the values, right? So if that happened in the last 3 weeks, then we just need to retrain our model, and that would be it.
No, I'm not sure where that's the question. Is it where we can apply this to manage like vehicles or that changes, whatever?
Like once you have different scenarios, like what if scenario, like once you have the model-based approach, all the equations.
I'd like to.
Yeah. The optimization.
What we'll do, can we keep that conversation to the end of
Sure.
and also when the speakers come, please come use the microphone because it's obviously being recorded as well. I'd just like to thank Angela for her presentation. I thought it was great. And now I'd just like to introduce Professor Rosalind Archer, the next speaker.
Thank you. So it's a real pleasure to be here. I really enjoy the spirit of the conference. So I'm going to offer a talk that goes in a slightly different direction. I'm an energy geek, I love crunching numbers, but I also like building bridges between science, technology, policy, economics, and people. So what I'm going to offer is really almost more of an op-ed reflecting on arriving in Australia from across the Tasman. My accent gives away that I'm from New Zealand, and looking at the differences in electric vehicle uptake. I would just like to briefly make an acknowledgement of country, acknowledging elders past, present and emerging, in particular the Gadigal people of the Eora Nation. So we'll start with a quick comparison between Australia and New Zealand. So I've got a few facts and figures on screen, sort of big picture stuff, to offer some context about why electric vehicle uptake in the two countries may or may not be different. You see differences in median incomes in terms of median hourly wage. Differences in housing stock are a little different, harder to quantify, but the difference in the number of people, percentage of people living in apartments wouldn't seem to be significant enough to drive a difference. Obviously, if you own an EV, having access to off-street parking and home charging is important. People think of Australia as this massive country, but actually when you look up the stats, both countries, we do about the same amount of driving per vehicle. So it doesn't seem to be that. Very different electricity supplies at the macro level, but obviously electric vehicles are often bought by people who have solar panels at home, who may have access to their own renewable electricity. But maybe just as a quick check-in on the audience, who in the audience would have access on their phone or on a browser to an understanding live of what your own home is doing in terms of electricity, in terms of usage, CO2 footprint? Who could find that on their phone in a matter of minutes? Only a few in this audience. And this audience is probably collectively energy geeks, and there's only a few that could do that. That's fascinating. So in New Zealand, if I ran that same poll in a comparable audience, we would get quite a different answer. So metering is much smarter and the data is much more accessible. Maybe one quick survey question. Who has access to time of use pricing at home? Wow. So if you're charging your EV, time of use pricing is fun. Time of use pricing means you can be incentivized to charge at 1 o'clock in the morning and avoid this big evening peak. So there are a few interesting kind of market issues there. So I have a clip there from The Guardian fairly recently, very recently, 18th of January, that accuses Australia of being in the slow lane with respect to electric vehicles while New Zealand accelerates ahead. So what is going on with that? So the real key is around policy and the intersection of sort of policy instruments. So this is actually research done by a group from UNSW that surveyed New Zealand drivers and looked at their likelihood of buying an electric vehicle as their next choice. So that's the scale on the y-axis, and on the x-axis, the type of driver they were. Are they pro-EVs in general or are they not? So they sort of segmented out the population as part of the study and showed that there are quite a significant group of drivers there who are pro-EV and are likely to make their next purchase as an EV. And then what comes in is one of the findings of that UNSW study was that New Zealand should go ahead with a proposed clean car rebate. So this graphic's off a government website where what New Zealand has done is to classify all our imported cars. We don't manufacture cars, so everything is imported in terms of its emissions, and apply a fee-bate system. So this fee-bate system means that if you have a car, sort of break this down into some examples of models cars you might be familiar with. So some of the EVs or hybrids, if you have a car that's cleaner than usual, you get a rebate from the government when that car is registered in New Zealand. And if you have a car that's sort of middle of the road, so there's some examples of middle of the road options there, Toyota RAV4 petrol powered. So if you're in that band, you don't pay anything and you don't get a rebate. And then if you're in the gas guzzling category, shall we say, you pay a fee. So if you want to drive a Toyota Hilux, if you want to drive a Ford Ranger, so if you want to bring one of those into this country, you pay a fee. So there, there's fees of on the order of $3,000 for some of the more polluting vehicles. And when this was brought in, it was meant to be a zero-sum game. That the modelling that they based it on predicted that the amount of income they would get from the charges on the gas guzzling vehicles would balance off the payments to the drivers of the electric and hybrid and other clean cars. So, what happened? The line to watch there is the red line, that big spike, that's the policy change. So this is off a government website looking at market share of electric vehicles, so that's percentage. So petrol cars have been dropping. Electric cars bounce when you get this policy. So new electric vehicles have huge market share in New Zealand. And the country has been very successful about continuing to bring them in. And one really key point about this doesn't only apply to brand new vehicles, it's new as in first registration in New Zealand. So you can import a 7-year-old Nissan Leaf from Japan and it qualifies for this. So we're not just subsidising Tesla drivers. But it wasn't altogether politically popular. It ended up becoming a somewhat polarising policy. So New Zealand has two major parties, National and Labour. Labour government is led by, till very recently, Jacinda Ardern. So the stats there, so about 15% of new light vehicle sales in New Zealand are electric, versus Australia at about 3%. The overall fleet is changing. We're getting there. We still have a long way to go, but our overall fleet is now 4.5% hybrid and 1.8% battery or PHEV. But this fee-bait mechanism that caused this big shift has been called a ute tax. So your big Toyota Hilux does attract a tax, and that has become a real political football. Jacinda Ardern, there's media coverage saying she considered ruling out those utility vehicles from the scheme. So if you're a tradie or a farmer who arguably needs those sorts of vehicles, they are taxed. And Jacinda Ardern ended up resigning as Prime Minister. I'm not necessarily drawing a direct connection between those. It's one of a family of policies that is popular with some in our community in New Zealand, unpopular with others. So ultimately we had a change of Prime Minister very recently. So I'd like to just say thank you for listening to those recollections from Trans-Tasman, and happy to take any questions or comments that people have.
Thank you very much. Any questions?
Thanks, Rosalind. Roger Dargable from Monash. In your first slide, you showed the difference in the electricity profiles, that you've got 80% renewables in New Zealand already, and that's mostly hydro, which is fully dispatchable, of course, and in Australia, the dominant technologies are wind and solar.
Yep.
And so there's a lot more variability in the output, and so to have a smart charging system in Australia have to be much more responsive, and every day will be different hours of the day. Whereas I'm wondering in New Zealand, because it's hydro, is the incentive still to charge your EV overnight when other demand is lower?
Yeah, I used to have time of use pricing, and then actually I moved to spot pricing, and spot was fantastic. I mean, electricity in the middle of the night was almost free some days. because we've wind on the grid as well. But yeah, our strong base of hydro does change the game a bit.
Yeah. And was your ability to have spot prices, was that automated with your EV charger, or did you have to manually decide when to charge it?
My spot pricing was just my regular electricity, both import and export. So my solar export would also track spot.
Right, but did you have a smart charger on your car that would take care of looking at the spot price and decide when to charge your car? So it was manually.
That would have been the next project if I was still in New Zealand.
Yeah, cool. All right, thank you.
Thanks for the press. So, here in Australia, we have a very funny situation where the time of use tariff, as defined by the poles and wires companies, is not reflected by the retailers, because the retailers just want to make money, and then they change for flat tariff because it's easier for customers to understand. But then that means the poles and wires have all these problems that the tariff are not reflecting what they want. So people do not use it at the peak time because the poles and wires cannot handle it. What's the situation in New Zealand? Thank you.
I mean, time of use pricing is very, very common, and one of the reasons I asked if people had apps or browsers on their phone is it's much more common there to have access to time of use pricing and just get an alert on your phone to say, hey, electricity prices are high, they're low, and to give you that nudge to change your behaviour.
Do you know where it is reflective of the time of use tariff of the poles and wires companies and the retailer? So the retailer are passing on that time of use tariff? That's really the key question here.
I believe they are, yeah.
All right, thank you.
Any other questions? Well, I'd just like to say thank you very much for Professor Archer, and everyone put their hands together. And now I'd like to invite you stand up to the speakers again, please.
Hi everyone, I'm Yushan Ho. I'm from the University of Melbourne. Today I'm going to talk about the effect of voltage unbalance on EV hosting capacity. So here is the outline of today's presentation. First is the context, and then I will show the methodology to study the effect of voltage unbalance on EV hosting capacity, and then is case study and key remarks. So now go to the context. So here is the simple feeders. Each phase have two customers, and one of them have an EV. So the voltage along the feeders among three phases, they are the same, and they drop little bit from the head to the end of the feeders. And so if we have two EV on phase B and only one on phase A, so there are still three EV, but two of them on phase B. So the voltage along the phase B will be much lower, and it may reach the lower limit. So the distribution of EV may increase unbalance and exacerbate voltage drop issue of certain phase. Here is phase B, and it may limit EV hosting capacity. So the question is that how unbalance caused by EV integration affects EV hosting capacity. So now, to answer this question, I will show you the methodology to study the effect of voltage unbalance on EV hosting capacity. I will not go into details. I just want to point out some important parts. So let's start with the beginning. So firstly, I will randomly select the profile for the loads, and then for each EV penetration levels, I will randomly do EV allocation. First, it will select the customers that randomly select customer with EV according to the EV penetration level, and then randomly select the EV charging size. And last, I will randomly select the EV charging profiles of the EVs. So here I'm used to simulate the cause of unbalance, that is given load behavior and potential uneven EV allocation among three phases. So now go to the impact metric and EV hosting capacity. So here for the unbalance I'm using voltage unbalance factors. So it is calculated using the voltage magnitude at head of feeders. And here's the 9 to 9 voltage I used to calculate. And here the maximum daily value is used. And the other is minimum customer voltage is related to the EV hosting capacity. The minimum customer voltage is used the minimum voltage of all the customers that belong to the same LV transformers. Here's it is the value at the time that the voltage unbalance factor reaches maximum daily value. And now let's go to the definition of EV hosting capacity. So it is the maximum amount of EV that a given distributed networks can host with the minimum customer voltage that within such a limit. So now goes the case studies. The case study, we use a real Australian LV networks. So for this network, we have 33 transformers, and the EV penetration level will change from 0 to 160%. 160% means that there are 60% of customers will have 2 EVs. And for each penetration level, we will take 100 runs. So I want you to have a look about the EV profiles. We can see that the EV charging profile have large difference, and this is very important, and I will also review this in the result. It will also be reviewed in the result. So let's go to the result. So next, the left figure shows how the voltage unbalance factor changes with the increase of the EV penetration level. We can see that from this figure, so most of the scenarios, the voltage unbalance factor is smaller than 2%, that is within the saturation limit. Oh, sorry about this, it's wrong for the template. So, and we can see that, and also the most important thing here, I want to show that with increase of the EV penetration level, the voltage unbalance factor keep increase. And here I want to point out is that for the 100% EV penetration level, that is every customer has 1 EV. So this one, the voltage unbalance factor is still larger than 80%. This is quite different from the results that we get in previously for the PV. So from the PV ones, we can see that for the 100%, it had the similar voltage unbalance factor of the 0%, that's the one that's without any PV. So this is because in the same region that the PV generation, they have the similar generation profile. However, for the EVs in the same region, they have the very large difference EV charging profiles. This means that it will bring larger larger unbalance for high EV penetration level. This is will bring more benefits if we reduce the voltage unbalance factors for EV. So now let's see the unbalance level vary among different transformers. So for these ones, we use one value to represent each transformer. That is the median voltage unbalance factor across 100 simulations. So let's have a look about 0% EV penetration level. We can see that there are 28 transformers in the relatively low voltage unbalance factor, that is 0.3 to 0.6%. And with the increase of the EV penetration level, the voltage unbalance factors of each transformer, they keep increase. If it sits 160%, there are 13 transformer in a relatively large range, that is 0.9 to 1.2%. And there are more importantly I want to point here is that there are large voltage unbalance difference amongst different transformers. So still look at the EV penetration level of 160%. So there are 13 transformers in the range of 0.9 to 1.3%, and there are 5 transformers in a very much larger range, that is 1.5 to 1.6. So when we do the analyze for the EV hosting capacity, we choose different transformer with different unbalance levels. So for the transformer number 13, which have a relatively small unbalance level, the maximum unbalance level is 1.3%. For number 5, have a very large one. Number 29 have even larger unbalance. So let's have a look of transformer number 5. So and let's have a look of when the EV penetration level equal to 100%. So This increase of voltage imbalance, so and the color will change from green to red and to dark blue. Here the color is representing the minimum constant voltage. So this means that the minimum constant voltage keeps decrease, and when it's more than a saturation limit, that is 216 volts, the color will change from green to red, that is, so which means that for the high voltage imbalance matters, imbalance factor, it will greatly limit the EV hosting capacity. Okay, so now let's compare different transformers. Here we select the same range of voltage imbalance factors, which is marked as a red box. So we can see that for the transformer number 13, there's no voltage issue, so the EV hosting capacity can go to 160%. However, for number 5 transformers, the maximum EV penetration level for this voltage imbalance range is 120, and for the transformer number 29, the EV hosting capacity can only reach 80%. This is so here is showing that for different transformer, even with the same voltage imbalance factor, they have different EV hosting capacity. So for the perspective of EV hosting capacity, we cannot, it's efficient to adopt a limit for the voltage imbalance factors. So if we set the maximum voltage imbalance factor as 1.3, for the transformer number 5, it can reach 120% EV hosting capacity. However, for transformer number 29, it cannot reach this EV hosting capacity. So now go to the key remarks. So first, the voltage imbalance factor keep increase as EV penetration level increase. So this means that the imbalance have a more important role in the EV hosting capacity than PVs, as PV will be imbalanced for the high PV penetration level. And the other is for the same transformer and the same EV penetration level, a high voltage imbalance will greatly limit EV hosting capacity and loss. And also the most important one, so the different transformer with the same voltage imbalance factor may have different EV hosting capacity. And from the perspective of EV hosting capacity, it is in effect to adopt a limit for the voltage imbalance factor. So that's all from my side. Thank you for listening.
Again, has anyone got any questions? And we'll save those up for the panel section then instead. Again, thank you very much again for your time. And I'd like now to introduce our last speaker, Subok, who's also from Monash University.
Okay. So, good afternoon. So this is my great pleasure to have this chance to present my work to you today. So my name is Subok Yoon from Monash University. So the title of my presentation today is GTB algorithm with voltage control for Monash microgrids. So let me talk about the motivation first. This graph shows the total amount of EV charging by AMO. So according to their scenario, the total EV charging will reach more than 60 terawatt-hour in 15 years. This is the more than 30% of total electricity consumption in Australia. So the aim of my research is to investigate the smart charging system to effectively handle this huge amount of charging while simulating this charging trend within the Monash microgrid, and thereby exploring the future potentials and business models of the GTP algorithm system. So this is a campus map of Monash microgrid. So we have 4 large parking space. So on average, up to 2,500 vehicles park in the campus. So my question is that if this number of vehicles changes to electric vehicle, for example, 10%, 50%, or 100%, so what happens to grid and how can we deal with the issues? So in my simulation, I have two scenarios. One is the reference charging, so there is no any control scheme, and my algorithm is the centralized algorithm, centralized one. So main control center, or called aggregator, is located in somewhere in the campus and controls all EV chargers and communicate with the main grid at the same time. So the logic of the algorithm is very simple, the load shifting. So the aggregator purchases the electricity from the market operator with spot price and sell the electricity to EV owners with fixed price. So the algorithm is trying to find the lower spot price period of a day and rearrange the charging schedule into the period. So in this way, the aggregator is able to minimize the purchasing price and maximize the trading profits. And for the EV chargers, I considered only two kinds of chargers: L1 slow charger and L2 chargers with 7 kilowatt charging power. And charging price of each charging system are different. And for the electric vehicle specification, I considered same model with the battery size of 50 kilowatt hour, and sampling number is up to 1,500 vehicles. The next objective of the algorithm is they are monitors violations. So in the simulation, there are two kinds of violation. One is main substation violation. That is the limitation of this line. So this is the limitation of size of transformer and line capacity. So total demand of microgrid never exceeds this limitation. Physically not possible. So next one is voltage violation. So this algorithm monitors the voltage magnitude by using root-and-rest method and trying to keep the voltage within the standard. So let me show you one example of main substation violation. So yeah, this is the this blue line. Yeah, this blue line means the base load of March microgrid in a specific day, and this blue bar means the total EV charging profile of 300 vehicles, and this is the total demand including EV charging. So if we increase the number of EVs, the charging total demand increase, of course, and in this case, this demand reaches level 4, 100%. The definition of 100% is the 100% capacity of this line. So total demand never exceeds this level, this limitation. So I define more than 95% of this capacity as a violation region, and the algorithm rearrange the charging schedule into like this. So the GTV charging is the total amount of the GTV charging is exactly same with reference case, but never experienced violation, and gets more daily profit because the most of charging profile focus on the lower RRP price. So this heat map shows the total number of main substation violations. So y-axis shows the number of EVs, and y-axis x-axis means the slow charger ratio. For example, this point saying that 300 EVs and 40% of slow chargers and 60% of 7 kilowatt chargers. And number one event, violation event in 2019. And so reference charging experienced lots of the violation event after more than 500 electric vehicles, whereas the GTP charging effectively controls the violation event, and so more volt range is available in this scheme. So next is the voltage violation. So if demand increased by the charging, the voltage decreases. So the algorithm detects this kind of the violation lower than 0.9 power unit. And if algorithm detect this kind of violation, they rearrange the charging schedule of this period into others. So as a result, yeah, so all voltage can be operated in the standard. So likewise, the previous vibration, GTV charging effectively controls the vibration event. And as a result, more broader range, broader scenario is acceptable in this case. So last one is financial analysis. So left is the MPV for 15 years for reference charging, and right is the GTV charging. So first, I'd like to point out in all cases, MPV charging guarantees better MPV. And if we increase the number of EVs, the MPV increases because the amount of the trading energy increases. However, if we increase the number of slow charger, the MPV increases a little bit up to 20%, then decrease rapidly. This is the reason why. This is charging achievement. So if we have too many slow chargers, on average, so EV owners can charge only 60% of their needs. So the total trading amount decreases rapidly. And for the IRR, if we increase the slow charger number, yeah, we can get higher IRR value, because this is the reason why the capital and installation cost of slow charger system is cheaper than 7 kilowatt charger. So considering all I mentioned above in this presentation, this is the possible area for reference charging, and this is a possible scenario for GTV charging, and this is the best case. 500 EVs, $3.7 million MPV, and 900 EVs and $6.6 million for GTV charging. So, yeah, GTV algorithm so can accommodate more EVs without violation in the microgrid, and this algorithm guarantees better MPV and IRR. So as a result, the broader range of business model is available in GTV scheme. So the infrastructure design is tricky and not easy to answer. So for example, more slow charger ratio is good in terms of the grid operation, but it's not good for people's satisfaction. So yeah, so more this is not only the technical issues, but also human behavior research. So more in-depth research is needed in the future. Thank you for your attention. Yeah.
Again, I'd just like to any questions?
Hello, thanks for your presentation. Are you running a three-phase power flow analysis? Because I noticed using level 1 and level 2,
Yeah.
considering I think it's a single-phase demand.
Yeah, that is the single-phase analysis.
Then
yeah.
when you're doing analysis, do you consider three-phase unbalance?
Yeah, so at that point, I didn't finish the three-phase analysis yet. Yeah, but so I like to point out how the voltage management algorithm, how my algorithm control the voltage management. So I like to express just the logic of the voltage magnitude.
So you are not just investigating the control algorithm, I think?
Yeah, so.
Okay.
Yeah, I can.
Because I'm a collaborator with Yushan, as you can see our study.
Yeah,
so if you consider unbalance, like certain phase can see more congestion issue or voltage drop issue, so it might help with your study.
Yeah.
Also, in terms of the level 1 charging definition, so here in Australia, I think level 1 you should consider up to 16 amp charger. So it's consider 230 volts is 3.7 kilowatt. I don't believe like in a public charging facility you can consider only 2 kilowatts. It is normally happen in home. So when people plug in to their wall charger socket, then the power will be lower. Yeah. So if you check the electric vehicle console configuration, there is such setting definition.
Yeah, thanks for your comment. Yeah, thank you.
Any other questions? All right. What I might do now is just invite all all four speakers to come up to the table and just open up to a panel discussion for wider questions. We don't have a long time for wider discussion, but has anyone got any questions they'd like to ask the whole panel or other some of the previous speakers as part of the process? And while people are all right.
Probably, can you hear me? Probably an observation to just get feedback. But you, Shan, I really like your presentation, but it talks to a future where the number of EVs that we have in Australia are going to grow, and there will be some suburbs where you're going to reach capacity earlier than others, which says where you buy your house could impact your ability to connect a car. And people are going to want to know that earlier rather than later. They're not going to want to buy a house, move in, buy a car, get home and find out that they're not allowed to charge from home because the transformer has already reached capacity. And we've talked for the last 2 days about the importance of bringing technology forward and tools forward. This is the sort of thing that really we need to start making people aware of sooner rather than later. Not right now, but as we increase our fleet, there's going to get to a point where we really need to have this sort of research and these tools available and visible to people and in a language that they can understand. Do you agree?
Yes, so, but still, what's your question?
Look, it's just an observation. I think that, this is important research, but I think it's research that we've got to turn into tools that people can use from a planning perspective so that they can see it when they're deciding where they buy their houses moving forward. Does that make sense? Does that make sense, Nando?
Yeah.
This is really pretty important. And I think it
I agree, Neil. I mean, at the end of the day, so far, we consider where's the next ramen station or the whatever station, and the distance of commute, if you are going to drive a car, to work, whatever, and other facilities, around the house, and of course the price and all of this, At some point, if electricity is going to become such a bottleneck in terms of your ability to put photovoltaics where you charge vehicles, that has to be mapped there. So somehow, the Poles and Wires companies, they need to provide a mapping that says you might face some challenges if you're planning to have an electric vehicle in this particular neighborhood.
Yeah, and I think it's not just EVs. I think it's capacity to connect more solar, capacity to connect batteries. And arguably, if we move to a transition where our households pay cost-reflective pricing, there could be better places to live on a feeder because you're closer to a transformer than being at the end of a transformer. I just think this is really, really interesting. I'd commend you for your work. Thank you.
Thank you.
Yeah, I mean, it is an interesting question that the Poles and Wires companies are going to have to lean into in terms of offering people that visibility. Yeah.
Well, actually, to go with that, maybe to open up to the panel is where do you see the key barriers and challenges for that need to be addressed as priority to facilitate the transition going forward for both EVs and also uptake of more PV, solar PV into the system?
I mean, as a starter for 10, I mean, obviously price and getting that price point to work at the lower end of the market. I'm not a particular fan of subsidising people who are driving, Teslas that are $60,000, $70,000, $80,000. That doesn't seem to make sense. If I wanted to own a Tesla, it wouldn't be a government subsidy that would make me do it. But if I want to buy a Nissan Leaf, it might be. I also would be thinking really hard about, what the system could do around housing and in particular rental housing. I'm now a renter in Australia. Getting EV charging into the particular home I'm renting would be very difficult. So I'm driving hybrid for now. But I would love to see housing policy that made some level of EV friendliness expected, at least in new builds.
That's a good point. Anyone else got any thoughts about challenges?
For the impact analysis we have to right now. So for the PV, so the first problems the discrete network met will be voltage issue, so high voltage, because we design for our networks for the loads is not inverter side. So for the EV, the first problem we all met will be conjunction. So there's discrete network first meet conjunction problem. So, and since all the EVs and PV systems, they all single phase, and so when we connect them, we don't consider the phase, so they will bring unbalanced problems, and they will make the distribution networks meet the voltage issue and congestion issue more quickly than we expect, because we usually expect them as balanced systems. So this is what I think from my perspective.
Yep.
Sorry, just to add on that, so you mentioned according to the AV hosting capacity related to the voltage issues. So we know that photovoltaics, once we integrate them, and there is a high generation, we have high voltage issue. There is also consideration of storage batteries. So I think considering all of these technologies together could solve some of the electrical vehicle negative, impact on the grid. I'm not sure if you consider that, or if you have any, thoughts about what could be like research thing on that to try to accommodate the disadvantage of the PV hosting capacity with the AV hosting capacity using the batteries, and might be some of the issues in the economic side as well for that. So just would like to hear your thoughts on that. Yeah, thank you.
So I think you're talking about coordinate all this kind of technology. So I actually think about it, and also we do some literature review, and for the research right now I'm doing now. So I think so. Sorry about talking about unbalance, because I'm a kind of unbalanced guy, so I'm always talking about unbalance. So for me, so solving these problems, we are doing three balances. So as you saying, that's using the storage, also the PV and EV together. And there are also another solution that's called changing the face of customer to the rebalancing. So when doing the comparisons, why think about whether we want to affect the customers, because if you do the storage, also do the EV management, PVs, we will affect the customers. So right now, I think the best solution is to change the face of customers doing, and this would have the smallest effect, and also alleviate this voltage issue and congestion issues.
Is that feasible from the economic side to change the phase?
Yes. So it's called phase switching devices. Yes.
So how do you actually educate consumers to actually understand what those issues are and the constraints that could be on them, and how do you manage their expectations? Because a lot of people are actually buying systems or buying EV cars and expecting them to be able to do what they want from these processes. Yet where we're talking through here that there are some issues there around constraints on some of these issues, and so how do we actually make sure that you don't lose the consumers, or you don't how do you actually manage their expectations to actually understand how we could take them forward? Any thoughts? Maybe from a New Zealand perspective, how have you been able to manage, particularly around the EV rollout, some of the issues around that?
Yeah, I mean, we're not yet seeing saturation type issues yet, but I know it keeps folks at the Lines Company awake in terms of, and they're kind of racing to get ahead of it with transformer upgrades in particular suburbs and particular parts of the grid that are weak. But yeah, so far, I mean, New Zealand hasn't seen that behaviour that it seems like Australia fears, that everyone's going to arrive home from work 6 o'clock at night, plug in, cause this sort of chaos of an evening peak. New Zealand hasn't seen that. From what they know about the charging patterns, it seems like charging behaviour is spread quite well. Either people like me who are charging in the early hours of the morning with a timer, obviously COVID and working patterns have messed everything up. So I had solar, could charge off my own solar at lunchtime. Yeah.
So is there something for us to learn then from New Zealand in terms of those behaviours to actually put into our...
Yeah, I think just the energy literacy in general around, things like time of use pricing being just baked into the fabric of what you do day to day as a consumer would help a lot.
Any other final questions? I know we're coming towards the end of the session. One last question.
Yeah, sure. So with photovoltaics hosting capacity, we have the issue of the curtailment. So once the voltage exceeds the voltage limit, the inverter can curtail. Do we have the same concept in electrical vehicles? Like if we have all the customers charging their batteries at the same time, is there anything blocking them to charge their batteries? Because that would make an under voltage issue. And is there any concept relating to, let's say, either curtailment penalty or charging penalty? Have you ever heard about something like that the DNSP should pay the customer something? Just to hear about the technical and the costing. Thank you.
Yeah. I mean, I know they were thinking really hard about this kind of stuff in New Zealand in terms of making the car effectively a service and having subscriptions to sort of trading relationships where you could hand over some level of control of your charging as essentially a service back to the grid, and they've just got to the point where we're trialling in New Zealand what's called multiple trading relationships, where you can actually have 2 electricity suppliers in or out of your house. So my electric car could essentially be a customer of one company and the rest of my house could be a customer with another to try and get that level of smart. Yeah, that's pretty edgy. There's a trial going on with that. Yeah.
Last question I've got from there is around impact around two-way charging on the grid, and because a lot of the stuff we've just talked about here is just one-way
Yes.
charging. Now we actually do get to two-way charging. One is it could actually have great benefits to the grid, but it could also have challenges depending on how it actually goes through. Just wondering the panel's thoughts.
So the vehicle to grid piece, it's still not common in either country, as I understand. I mean, there's trials going on. New Zealand's been trialling vehicle to grid since 2019, and they've been focusing it in places where the grid is weak. So, ironically, this week with the floods in Auckland, one of the vehicle to grid locations will have come to the fore in terms of keeping a remote beach community online.
Anyone else got anything? Well, if that's the case, I've come to the end of the session. I'd just like to thank the 4 speakers today. I think it's been great. Good conversation, great things that we've learnt from it. So people can put their hands together for the